Welcome to the debate. Today we're diving into something that honestly feels like a persistent wall in modern machine learning. It's this problem of latent learning, or maybe the lack of it.
Right.
You train these huge models, LLMs, agents, whatever. They absolutely nail the explicit tasks you train them on. Score high on seeing goals, spit back definitions perfectly. But then you ask them to do something slightly different with that same information. Ask for a reversed fact, maybe point them to an unseen target in a maze they supposedly learned, or encode something using a rule they learned only through definitions.
Yeah, they just fall apart.
Exactly. Performance just collapses, often near zero. Like, that feeling when your code almost works but gives you nonsense? It's like that, but for knowledge reuse.
Mm-hmm.
And this isn't new, right? This echoes way back to cognitive science, like Tolman's rats learning maze layouts even without a reward, that latent knowledge they use later. Our AI systems, well, they seem stuck learning only what's immediately task relevant, not stockpiling knowledge flexibly for the future.
Okay.
So the core question, the real debate today is, I think, architectural. We've seen these impressive results where augmenting models with non-parametric episodic memory, basically a system that lets them look up relevant past experiences, like an oracle, fixes this latent gap. Does this success mean we need a fundamental shift towards something like a complementary learning systems or CLS architecture, like in the brain? My position is yes. I think these failures are structural, inherent to how current models learn, and they demand the flexibility of a separate episodic system.
And, well, I see it differently. I absolutely agree the results are striking. Retrieval is clearly a powerful tool, maybe the most powerful tool we've found so far for this specific latent gap problem. But I'm just not convinced this automatically translates to architectural necessity. I think what we're seeing might actually be the result of incredibly sophisticated meta-learning happening within the existing transformer models, specifically really robust in-context learning, or ICL. From my perspective, retrieval is acting like a very, very effective form of data augmentation, feeding the right context to this powerful ICL mechanism. It's not necessarily proof we need a whole separate system built in.
Okay, let's get into the positions then. For me, the argument for architectural necessity comes down to the inherent rigidity we see in standard parametric learning. Using gradient descent, the knowledge seems to get baked into the weights in a way that's tightly coupled to the original task format. It's not that the model forgets the information, it often demonstrably knows it.
Right, it can recall it.
Precisely. It can recall the definition or it can solve the task if you literally hand it the missing piece of information in its context window. But it fails the latent test, applying that stored knowledge spontaneously to a new goal or format. Retrieval, acting like this episodic memory buffer, effectively bridges that gap. It turns, say, the impossible reversal without context problem into the easy reversal with context problem. It's providing a fast, flexible route to reuse specific past experiences, which sounds an awful lot like the proposed function of the hippocampus complementing the neocortex in CLS theory. It unlocks inflexible knowledge for flexible reasoning.
And I'd frame it this way. Yes, retrieval works, but let's look closer at how it works in these experiments. It takes a specific, relevant past sequence and shoves it into the model's input. What happens then? The model uses its in-context learning ability, honed during training, to process this combined input and arrive at the answer. The paper itself points out how critical within-example ICL training is for retrieval to succeed. So if the model has to be explicitly trained on how to make use of these retrieve sequences, if it needs to learn the pattern of, say, using a forward statement to answer a backward question within its context window, then isn't the core skill, the flexible reuse part, actually being handled by the parametric system's meta-learning? Retrieval is just a very clever way to provide the perfect input queue. It's feeding the ICL mechanism what it needs. The failure without retrieval, then, isn't necessarily an architectural lack, but maybe a gap in the meta-learning training data or process, maybe solvable with better training augmentation, not necessarily a whole new memory module.
Okay, let's dig into the codebook's benchmark, because I think that really crystallizes the rigidity issue. This setup is quite elegant, I think. The model learns definitions like latent index A means perform operation B. Simple enough. Ask it to define A, baseline model nails it. high score. The knowledge is clearly in there, consolidated in the weights.
Okay.
But then, the critical test. Give it a new input, C, and ask it to encode C using the rule for A without reminding it of the definition A means B. The baseline model just fails. Performance tanks near zero. It cannot take the knowledge A means B learned for definition tasks and apply it prospectively to an encoding task. Retrieval, though. You add the definition A means B back into the context via retrieval, and boom, accuracy jumps right back up. It uses the old context for the new task. That, to me, feels like a fundamental inability of the parametric system to repurpose knowledge across formats, not just a tough generalization problem.
I see why codebooks looks like strong evidence, but I'm still hesitant to call it proof of a fundamental incapacity. It's definitely a failure of generalization, a very sharp one. But the comparison feels a bit loaded, right? We're comparing a standard model against one given oracle retrieval, perfect context, every time. That's a huge advantage. And think about the semantic structure benchmark results. There, baseline models actually could generalize reasonably well on reversals if you gave them strong associative cues.
But that's the point. It needed the cues.
Well, yes, but if the model was truly architecturally incapable of accessing that latent knowledge, those cues shouldn't have helped at all, should they? The fact that performance degrades as cues weaken suggests it's more about the difficulty of accessing or triggering the right knowledge pathway within the parametric system. It hints that the capacity might be there, just buried or not sufficiently trained for spontaneous use without strong prompting. And remember the ablations showing that just throwing more data, bigger batch sizes at the problem didn't fix it? That tells me it's not about quantity, it's about the kind of training, maybe needing more diverse meta-learning examples, not necessarily a separate memory store. And this brings me back to the role of ICL training, which I think is really central here. Let's look at figure 7 in the source material. That experiment is quite revealing. They took the simple reversals dataset and specifically removed the training examples where both the forward fact, Plato taught Aristotle, and the backward relation, Aristotle was taught by Plato, appeared together in the same context.
Right, the ICL-like sequences.
Exactly. And what happened, even with oracle retrieval providing the forward fact, the model's ability to answer the reversed question plummeted. It dropped to something like 12% accuracy on the latent test. Now, if retrieval is the architectural fix, the hippocampus analog, why does it suddenly become almost useless when the transformer, the neocortex analog, hasn't explicitly learned the trick of using context A to solve related but different problem B during its own training? This, for me, strongly suggests the parametric model is learning the actual algorithm for memory use via ICL. Retrieval just provides the data for that learned algorithm. It feels like we're potentially mistaking a sophisticated learned processing strategy for a need for new hardware, so to speak.
Okay, I see the point about the ICL dependency, but I actually think that strengthens the CLS analogy. It doesn't weaken it. Think about how these systems supposedly work in the brain. The hippocampus isn't doing all the complex reasoning itself, right? It's often thought of as an index, something that points to or reactivates the relevant neocortical representations of a past episode.
A memory index. Sure.
Right. So the retrieval mechanism here acts like that index. It finds the relevant trace, the specific past experience. But then the neocortex, or in our case, the main parametric body of the LLM, has to do something with that retrieved trace. It has to apply its general reasoning abilities, its learned ICL capabilities to that specific piece of context. The failure you highlighted when ICL sequences are removed from training doesn't show retrieval is redundant. It shows the system hasn't learned how to integrate and process the information provided by the episodic memory system. You need both components, the memory system to provide the specific data and the reasoning system to flexibly operate on it. Learning to use the retrieved memory via ICL is part of making the complementary system functional. And let's not forget the cross-domain aspect. This isn't just fixing quark-fin language models. The same retrieval mechanism proved effective for the reversal curse in LMs and for the latent grid world navigation task. This grid world task, which is directly inspired by Tolman's rat experiments, was failing in both behavioral cloning and reinforcement learning agents. Retrieval helped them find those latent, unrewarded object locations based on past explorations.
It did improve performance.
Right. The fact that this one principle, flexibly reusing specific past experiences via retrieval, works across language, BC, and RL suggests it's addressing a pretty fundamental limitation of standard gradient-based learning, regardless of the domain. And think about the flexibility advantage. Training time augmentation requires you to guess upfront all the possible ways knowledge might need to be repurposed later. Retrieval doesn't need that guesswork. It queries the memory store at test time based on the current need. That feels inherently more powerful, more like learning for the future in an open-ended way.
Okay, flexibility is the big selling point. I grant you that. But we have to be realistic about the implementation cost here. We're talking about an Oracle retrieval system in these studies. Perfect recall, perfect relevance. Building an effective, scalable retrieval system in the real world is, well, it's a huge challenge. Indexing, searching, latency, relevance ranking, these are massive, unsolved engineering problems in many contexts.
Fair enough. The Oracle is an idealization.
Right. And training time augmentation, while maybe computationally heavier during training, completely sidesteps that complex, potentially brittle test time retrieval process. It amortizes the cost. And even in the grid world experiments, the paper notes the results with retrieval were far from ceiling. Using episodic memory effectively for complex sequential decision-making like navigation is clearly much harder than just recalling a fact for a reversal. So while the principle is powerful, the practical path to making it work robustly, compared to just improving the parametric model's inherent generalization via better training, is still, I think, an open question. We need to weigh the theoretical elegance against the practical complexity.
So to wrap up my view, the consistent pattern of failure on latent tests across different tasks, codebooks, reversals, grid worlds, where models know the facts but can't reuse them flexibly, points to a core limitation in parametric learning. Episodic retrieval provides a clear, functional solution, acting as a necessary complementary system that supplies specific past context, which the parametric system can then process using its learned ICL skills. This aligns nicely with the complementary learning systems framework from neuroscience and seems essential for building AI that can truly learn prospectively.
And from my side, while retrieval is undeniably effective and leverages ICL in a powerful way, calling it an architecturally necessary component feels premature. The critical dependence on the parametric model, having already learned the how of using context via ICL, suggests the core flexibility might reside in meta-learning within the transformer itself. I think we still need to explore the limits of purely parametric solutions, perhaps through more sophisticated meta-learning or systematic training time augmentation, before concluding that a separate memory system is the only way forward. The practical challenges of real-world retrieval systems also temper the appeal of this architectural shift for me.
Well, regardless of where we land on architectural necessity, it's undeniable this line of research gives us a very strong reason to keep investigating non-parametric memory in AI. It really sharpens the questions around where knowledge actually lives. Is it locked in the weights or flexibly available in context?
Absolutely. Understanding that boundary and how to effectively bridge the gap between consolidated knowledge and flexible, future-proof application is definitely a critical frontier if we want to move AI closer to the kind of robust, adaptable intelligence we see in the natural world.